In section 13.1, we used calculators and tables to guess the values of limits, particularly ones where the limit or the value of x that we were looking at made the original function undefined. Well, we can also find limits algebraically. So here are some properties of limits that help us when we're calculating limits algebraically. The limit of a sum, you can add the limit of two different functions, or you can add the two functions, then find their limit. The way the limit of a difference works, you can subtract the limit of both f of x and g of x, or you can subtract the functions and then find its limit. The limit of a product, you can multiply the product of the two limits, or you can multiply the two functions, then find its limit. The limit of a quotient, the only thing you need to remember is that the denominator cannot be 0. So if you have a limit of a function that goes to 0, it cannot be in the denominator of the fraction. You can either divide the two limits, or you can divide the functions, then find their limit. The limit of a constant multiple. You can find the limit of a function that's been multiplied by c, or you can find the limit of the function and then multiply that answer by c. The limit of a power. You can find the limit of a function that's been raised to a power, or find the limit of the function, then raise that answer to a power. And the limit of a root. You can find the limit of a function where you've taken the root of it, or you can find the limit of the function and then take the root of that answer. In example 1, let's use the limit laws and the graphs of f and g in the picture to evaluate the following limits if they exist. So let's start with the limit as x approaches -2 of f of x plus 5g of x. Let's actually find the limit of each function at -2. And then I'm going to add the limit of f of x plus 5 times the limit of g of x. So the limit as x approaches -2 of f of x. So here's where -2 is. F of x is the red function, and it appears that it's approaching 1. Then the limit as x approaches -2 of g of x. G of x is the blue function. Well, as I approach -2 from both directions, it appears the output is -1. So the answer is going to be 1 plus 5 times -1, which is -4. All right, I'm going to go back and do this again. But this time we're going to find the limit as x approaches 1 of the product of f of x and g of x. So the limit as x approaches 1 of f of x times g of x. So again, what I'm going to do is I'm going to find the limit of f of x and g of x at 1, and then I'll multiply those two answers together. So here's 1. So the limit of f of x, it appears as if I go from both directions that the y value is 3. And then at g of x, if I approach 1, wait a second, from both directions, the y value that I'm approaching has two different values. So I guess that if the second function's limit does not exist, then the limit of f of x times g of x just does not exist. All right, now I'm going to go back. And the next one, we're going to do the limit as x approaches 2 of f of x over g of x. In order to do this, we're just going to find the limit as x approaches 2 of each of those functions and then divide it. So here's 2. So the limit of f of x as we approach 2, maybe that's at about 2.5, or 2.5? Yeah, maybe we'll call that 2.5. It's somewhere around there. So the limit in the numerator is 2.5. The denominator, as we approach 2, you'll notice that it's on the x-axis, which means the output is 0. Wait a second, I can't have 0 in the denominator of a fraction, so I guess that limit does not exist. All right, let's go do one more. This time we're going to find the limit as x approaches 1 of f of x to the third. That means that we're going to find the limit of f of x at 1, and then we're going to take that answer and we're going to cube it. So at 1, the limit of f of x is 3. Well, all I'm going to do is take 3 and raise it to the third, and the answer is going to be 27. When we apply the laws of limits to find limits algebraically, we need to look at some special limits. The limit as x approaches a of any constant is just that constant. The limit as x approaches a of x is just going to be a, because you literally plug in a for x. The limit as x approaches a of x to the nth power is a to the nth power, because again, you just plug in a for x. And the limit as x approaches a of the nth root of x is the nth root of a. The easiest way to do a lot of limits is to just plug in the limit into the function and find the output. As long as the value that the limit is approaching does not make the function undefined, the easiest way to find a limit is to literally just plug that number into the function. It's just substitution. So because 5 will not make 2x squared plus 3x plus 4 undefined, I'm just going to plug 5 in for x. So 2 times 5 squared minus 3 times 5 plus 4 is going to be 39. In part B, think about what would make the function undefined. You would need to get a value of 0 in the denominator. But plugging in -2 for x will not give you a denominator of 0. So therefore, the easiest way to attack this problem is to just plug -2 in everywhere you see an x. There are other ways that the book did this. The book actually found each limit individually. I don't know why you would do that. For this problem, the numerator would become, let's see, -8 plus 8 minus 1, which is -1. And the denominator would be 5 times, this would be 5 plus 6, so that'd be 11. So the answer would be -1 over 11. These kind of limits where you can just plug the number into the function is called limits by direct substitution. The only time that this works is when you know that you're not going to get 0 in the denominator of a function. So, in example 3, the limit as x approaches 3 of 2x cubed minus 10x minus 8 is done simply by just plugging in 3 everywhere you see an x. And then finding out that the answer is 16. Sorry, I didn't mean to put that there. In part B, -1 will not make the denominator 0 because -1 to the 4th power is 1. 1 plus 2 is 3. So direct substitution would give me, let's see, 1 minus 5, which is -4 in the numerator. And we just said in the denominator, -1 to the 4th is 1 plus 2 is 3. But what happens if direct substitution does not work? In example 4, if I were to plug 1 into this function, the denominator becomes 0. So I need to find another way of attacking this problem. Well, one way of attacking this problem, if it is possible, is to try factoring. And I want you to notice that the denominator is in the form a squared minus b squared, which tends to pop up quite often. In factored form, it's x plus 1, x minus 1. Well, what ends up happening is these end up canceling. So the point of discontinuity here was a whole. X is 1. Well, now I'm left with finding the limit as x approaches 1 of 1 over x plus 1. Now I can plug 1 into the function, and I find out the limit is 1/2. What if factoring doesn't work? In this problem, the limit as h approaches 0 of 3 plus h squared minus 9 all over h. If I plug in 0 by direct substitution, I'm going to get 0 in the denominator. I can't factor. So what I'm going to try with this one is I'm going to try to actually just multiply it out. So 3 plus h, when you square it, is 9 plus 6h plus h squared, and then there's a minus 9 here at the end. Well, these 9's ends up canceling out, and the two remaining terms are both divisible by h. So I'm left with the limit as h approaches 0 of 6 plus h. Well, now I can plug in 0 and not get undefined. I get 6 plus 0 equals 6, so the limit is 6. In example 6, again, I can't put 0 into the function because I'm going to get 0 in the denominator. It's got a square root in it, so I can't factor it. But I lost my calculator, so I can't graph it. What am I going to do? Well, this problem is actually really important because this is going to pop up in calculus quite a bit. We're going to do something that you've done before, just not exactly in the same way you've done it. Remember when we ran across problems like 2 over the square root of x minus 5, and we said to you, rationalize the denominator? The way that we would rationalize the denominator is we would multiply by something called the conjugate of the denominator. The reason we did that is because now when I multiply these together, those are in the form a squared, or a minus ba plus b. When you multiply them together, you get a squared, which is going to be x, minus b squared. And your radical's gone. Instead of rationalizing the denominator, though, what we're going to do in this problem is we're going to rationalize the numerator. That means we're going to multiply by the conjugate of the numerator. And the conjugate of the numerator is going to be the square root of t squared plus 9 plus 3. I know, it doesn't look very pretty, but remember that when you multiply these together, this is a plus b, a minus b. You get a squared, which means when you multiply those two square roots together, the square roots cancel, minus b squared. And I'm not even going to multiply out the denominator. I'm just going to leave it written like this. So now what happens is those cancel. And then there's a t squared in the numerator, a t squared in the denominator. Well, guess what? They cancel. So now you're left with the limit as t approaches 0 of 1 over the square root of t squared plus 9 plus 3. Now when I plug 0 in here, I'm not going to get undefined. Because when I plug in 0 for t, that just becomes the square root of 9, which is 3, and I get 1 over 3 plus 3 is 6. The limit as x approaches 0 of the absolute value of x is pretty easy because if you plug in 0, the absolute value of 0 is 0. But I'm going to show you another reason that this happens. We need to go back to exactly what the definition of the absolute value of x was. The definition of the absolute value of x was that it was equal to x if x was greater than or equal to 0, and it was equal to negative x if x is less than 0. What that meant was when I graphed it, this was the graph of y equals x, but only y equals x when x was greater than 0. And then the second part was the graph of y equals negative x, but only when x was less than 0. And the graph of negative x looks like this. Well, that's where our V shape comes in. So one of the other things I could have done is I could have looked at the limit from the left and the right. And if you look at it from the left and the right, you'll notice either way it's going to go to 0. One of the definitions of a limit of a product was that it's the same as the limit of the numerator divided by the limit of the denominator, as long as the limit of the denominator was not 0. So in example 8, the limit as x approaches 0 of the absolute value of x over x. If I take the limit of the numerator, we just did that in the previous problem. We found out it was equal to 0. But no matter what way you cut it, the limit as x approaches 0 of x is 0. And since I can't have 0 in the denominator, this limit must not exist. If you think about this in terms of graphing, if you had graphed this as the absolute value of x divided by x, you would have seen the graph look like this. And we know when you're approaching 0 from both ends, if both ends of the graph go to two different y values, the limit does not exist. However, if I had just asked for the limit as x approaches 0 from the left side, it actually would have had an answer, and the answer would have been -1. Or if I had asked for just the limit as x approaches 0 from the right side, the answer would have been 1. Those are those one-sided limits that we talked about in the previous section. But as a whole, the function does not have a limit. Finding the limit of a piecewise function is very simple. F of x is the square root of x minus 4 if x is greater than 4, and it's 8 minus 2x if x is less than 4. What I want you to notice is that neither one of those functions actually exist at 4. Remember, the inequality symbols that do not have the line underneath mean that it does not include that number. So that means technically it's an error message there. But we can still find out what y value you're approaching. Algebraically, all you have to do is plug 4 into the first function. You get the square root of 4 minus 4, which is 0. And then you plug 4 into the second function. 8 minus 2 times 4 is 8 minus 8, which is 0. Well, if you plug in 4 to both of those independently and they both equal 0, then the limit must be equal to 0. You can also check that by graphing. Remember, you can plug this into the graphing calculator by doing y1 equals the square root of x minus 4, division sign parentheses x greater than 4, and then graphing y2 equals 8 minus 2x, division sign x is less than 4. And when you look at the graph, you'll see something that looks similar to this. And then that will be at 4. And you'll notice at 4, it hits the x-axis, which means the y value is 0. And that is finding limits algebraically.